Scarpinci will take over from there. I'm very pleased to present the first speaker this morning, Dr. Celani, who will speak on the effect of gamma beta phase interfaces on the hydrogen deuterium palladium overloading. Thank you.
Okay. So this work was made in collaboration with our historical group in Asami, together with some company, private company, and together collaboration with the Gavi, the company Will, and long-time collaboration with NATO NHA collaboration. And one of our member group spent several months in the support. The outline of my work is a little bit full because we try to understand why there is so large irreproducibility of this system. So we come back to vast study, very elementary, and analyze each aspect and try to find the reason and a possible solution. So before the effect, I will speak about well-known electronegation formula. Moreover, I spend some words about the effect of the diffusion speed. You have the last point? Speak about the experimental aspect, that the diffusion speed of hydrogen or deuterium in Palladium change very much according to the loading. Moreover, another not well-known explored aspect that is, according to our experience, the main problem in using electronegation formula is how to maximize the ratio between the voltage applied on the wire and the effective wire temperature. This is a key point of all the problem. I make some short memory of the previous experiment using pulse electrolysis power specialty way. We get quite a reasonable chassis, but a very poor understanding how to optimize this one. With a way our cell is like a black box. We give some pulse, some frequency, some amplitude, and that is what happened. But the understanding was not satisfying according to our group. So we move for just for understanding to DC high voltage electrolysis. Chassis drop a lot, difficult to have some big value. Only few times from inside the system give very large chassis for quite enough long time, but usually little or nothing. But understanding was very good. So because this modern ways does this aspect, now we can say something more about this complicated experiment. Another strange variant we observe almost always we use long wire, that at the beginning of the experiment, the most cathodic side of the wire load better than less cathodic. This is what expected. But when the situation is reversed for some unknown parameters, it will be solved the problem. The heat always disappears. We think that the most cathodic can work because there are some natural barrier at the end of the wire, but it's not stable over time. And I will explain how we can make a more stable barrier. and speak about the true wire temperature, how to control it and to measure it. Moreover, we have found experimentally that we have a local boiling of the heavy light water and heavy water on the wire, even the apparent temperature of the cell is only 20 degrees. This aspect is for some points good or dangerous, because when the boiling, we make usually calculation for 1 cubic centimeter, 4.2 joule, but the boiling we have more than 2,000 joule for 1 cubic centimeter. So we underestimated very much, but of 500, the heat going out. So apparently we have negative balance, but this is the reason. After that we show what is the value of high voltage electrolysis at low current in respect to the conventional high current and low voltage. Speaking a bit about the problem aspect of impurity of the surface, how this can help in some respect. And some picture about our new setup in order to decrease the waiting time for the manipulation of the calorimeter. And the left, working for almost 1 year with the light water, we found that in some proper condition there is a large enhancing of enrichment of deuterium inside Palladium wire. One proper excitation is given to the wire. It's completely new and expected result. And now the last argument is we start some experiment a few days before coming here with the new calorimeter, and we found the boiling effect after several hours from starting point. A conclusion. So, some attention, this is a well-known electromigration formula. What is important is this ratio between the voltage applied and the temperature. Otherwise we cannot control, because it is also constant if charge and so on. And the other aspect that I want to, and we use it, is different diffusion speed in the alpha phase, about 10 to the 5, beta phase, low diffusion speed that we will use, and the gamma phase will happen very fast diffusion speed. So, which one is the reason to use thin wires, thin, because we want the large we want to maximize the ratio of voltage over temperature, wire temperature. So, we want to maximize voltage, and it depends on inverse of diameter of the wire, power of 2. But the temperature effective of the wire depends on heat exchange of the system. So it depends on the ratio between the surface of the wire over volume. So again, 2 power divided here. Combining, it can be shown that this ratio depends on the reverse of power 3 of the radius of the wire. Very, very strong difference. So means if we go from our typical now 50 micron to 500, mechanically very stable, we want this ratio of 10 to 3. Shortly, I want to present what we have done up to now. We use Passell electrolysis, long and thin wires. Before was just technological aspect. We have seen that the wire was long and thin the system did more HSC, so just technological aspect. And we used high power pulsed electrolysis, very fast rise time of the order of 100 to 109 nanoseconds, some proper frequency range, and with some proper duration. We used Palladium alloy, and we tested several wire diameter, and we found when the wire was smaller diameter, all worked better, and when the last time the system was fast. So we get some enough good result about HSE, but to understanding was really not enough. So we decided to come back in some way to the CA electrolysis in order to better understand the system. It was shown during that conference in Sapporo. So we adopt a longer wire with 5 pickup points. We overimpose a AC current in order to measure the resistance and try to understand what happened. Schematically, this was the cell, the system we used last year in Sapporo. Here is the cell. Palladium is like a long resistance. Here DC power supply system, assignation to resistance, AC current sink, so the current can go to this capacitor, and here, when necessary, we increase the spontaneous electromigration with this set of auxiliary planets when necessary. Speaking about this easy to understand system, we have in steady condition typically not so large HSC, maximum about 10%, usually less. But this HSC increases from itself in some non-equilibrium condition. When we switch off the system, short time after give again power. So from itself give large HSC of the order of 100 watt, and with a large energy gain over 200% and several hours, so we can make any kind of control we want, even with the conventional mercury thermometer, to be sure. So these large conditions were not still errors, but we could control in DC. Just wait, make something strange, and sometimes start being wonderful. This is one of our best results in DC condition shown in Sapporo. So the system, this was the resistance, the gain was 0, so this means no gain. This time we switch off the system for a few seconds, the resistance ratio increases and drops very, very quickly, so it's loading. And during this time, the gain increase very much to 200%, and after spontaneously decrease. So we again tried the same procedure, so it is more 10 hours, 12 hours experiment. But this time the effect was weaker, but 80 something, but again this go to 0, try to start, but the third time was 0. So very big effect, but the control very weak. So I want to introduce, we had 5 pickup points, means 4 resistance, and we found that at the beginning of the experiment, the most cathodic side of the wire always loaded faster and higher value than less cathodic. and then this is what expected, nothing strange. According to electron formula, delta voltage equals the Y, and tougher loop, because we have a larger current on the most cathodic. But after sometimes, maybe hours, days, never, but very rare this one, we have a reversing of the condition. It means the most cathodic is loading weaker than the less cathodic. It is completely in disagreement for what we expected. And this kind of behavior is common with hydrogen and deuterium system. In what we are interested that when it is anomalous happen, the HS field always disappears. Even low level always go to zero or bit negative. So when the less cathodic is better than the less cathodic, the most cathodic, the HS field disappears. So is in time log scale just to the idea, acceleration, the deuterium, most cathodic, go faster, reach maximum, and that decrease. In this region, we have, if the loading is enough, a HS field. When time lapse, while usually spontaneously decrease loading, and when we observe the less cathodic, this is what expected with the theory, but later the less cathodic is better than most cathodic. But in this region, the HS field disappears. So we try to understand what really happened, what is a very strange phenomenon. So we realized that there was some effect due to our mechanical construction of the system, how to soldering the wire. We soldered with a thin lead conventional Palladium wire with the copper wire and make some glue to insulate and so on. And we found that how we make this arrangement of the cell, the preparation, has some effect of the final loading. So this was important for us, changing the procedure from myself, Monty, I asked to a student, the result was very different. So we need something back inside. So what we realized, the glue and the copper or the some effort, so over time the glue over the point was dissolved. The glue is like a barrier, and we realized when we take off some experiment, the wire when after this reverse condition is due to this barrier that changed the condition. Try to understand what is in more detail, possible explanation. This the neck wire here as a final soldering. So in this area, the temperature and the barrier are different in this session. So there can be a accumulation of deuterium in this section, the most cathodic. But this side is more stressed. So after some time, this go out completely destroyed. So works this one. But the longer time, this one they destroy the two, so nothing happens more. It means in this session we have a gamma phase, we have large loading, large diffusion speed. It is like a barrier because the glue reduces the deuterium income, so this area can be in alpha or beta in the beta phase. So we have a factor of 100 about diffusion speed. So this area, the value can connect just to this. So this is the active section of the wire, just this interface. So in some way, the Palladium is like, we see like a tube, what is very good inside, and the S barrier. This works because the Laplace constant are very similar in gamma phase and beta phase. Just to remember what happened, when this light condition happened, we have that the beta phase remove the increasing gamma of gamma phase. When the exposition is properly used, but the other problem is the thermal diffusion. So if the effective white temperature of the beta phase is too large, this effect is not useful. So if we have barrier at enough cold temperature in the beta phase, we have some dynamic condition, we have to check it. So meet these three parameters is not so easy job. Just want to show some very old data from students of Cohen in 1931. So he used thin palladium wire the micron with hydrogen, maybe in the beta in alpha or beta phase, and they measured the diffusion speed versus temperature. When he applied large voltage drop, 1 volt centimeter, diffusion speed increased about 1 order of magnitude. So this long, very old observation give us some idea how to manage the situation. So we built a very simple experiment. We ran light water to avoid error due to some chesit when happened, and optimize this kind of study. So it was long about 30 centimeter wire. The center section was no cover, and we covered both ends of the wire with some proper material. And we ran in anodic condition with poor water and study what happened in the system. So to protect the finesse section, we use a shrinking tube for this section and this section because it's more stable in respect to the loop. This system gives us some good result, but again, large irreproducibility, even with hydrogen. Sometimes we get really large loading in the central section of the wire, but most of the time the results without covering were better than with the covering. So to reach the better result is in the covered section, the temperature increased very much. Temperature increase, diffusion speed increase. So we think we works in the covered section in the beta regime, but high temperature. So was worse than using NAC tube and just old barrier with silver and blue. This is the reason why the overall dependent effect, because changing how to shrink the tube, we change a lot the real wire temperature. We found a solution which is coming from electronics world. So we make some thermal conducting silicon grades around the wire. In that we we use a shrinking tube. In this way, we reduce it strongly, the temperature increasing, and we make the system quite very close simple. This is some, okay, we use it at the convention when we follow how to calculate the true wire temperature. This is made in this condition, so high accuracy. The green one is the tube nail without covering, the red one with the covering, and the blue one covering and grease. And we started to 300 milliampere of electromagnetic current in air. So we moved from only 10 degree increasing, the best, to 150 there was with McKubre. So very big changing and improvement. It's equivalent effect of resistance increasing, so the McKubre, larger resistance increasing, the cover decrease lower. Is the intermediate just covering in air. Just an idea, the power dissipated in the system, in the cover, at 300 milliampere in air, we have about 4,000 watt per cubic centimeter, and it don't break. So it's good point for other future application. Our density. We repeat this experiment in water. Our interest lies in water, and here we found that the heat change of make tube wire is better, so lower temperature, but it reaches gamma phase. This is the covered and grease, so the difference is not so much decreasing, and just covered. So it's different in the log scale, a big changing. So it explains why the overload dependent effect about loading or deloading, a big changing. This is about the reproducibility. The two wire temperature of two sections, the data are really the same. No difference between the night tube, the night wire. This comparison resistance changing. Grease covered and just covered. Giant effect. Again, about power density that we can manage safely with covered with a night tube about 40,000 watt per cubic centimeter. Here about 50, here covered, only covered 100,000 watt, but here the wire was broken. Covered, limiting 100,000 watt per cubic centimeter. Very big power. Palladium is not so weak as expected. This experiment is more strange. We take off all the covering and increase the current to the order 100,000 ampere per square centimeter. Use pure water, anodic, and no covering. Resistance ratio increasing current, and that strongly change the shape, and here too, it is about 1.2 ampere to change it. So we want to understand this kind of value that can be used. We found that so the back temperature was only 20 degrees, that keep constant as much as possible, at about 1.5 ampere. We have two wire temperature about 85 degrees larger than beginning. So it is just a boiling point of water. The reason why this change of the drop, because locally the wire has boiling field. And you can hear, because the wire make a big noise like explosion continuously. It works exactly up to this 2.1 ampere. So it's even it's very chaotic and noisy explosion really. The wire is not destroyed. So boiling point system. This curve is a little bit not so common, and we try to find some optimal point about this how to increase the voltage without increasing the temperature. So because we think the voltage is controlled electromigration, so we use for loading and defeat. Temperature is just chaotic for the loading. So we want to maximize this ratio, voltage over temperature. Time? Okay, so this curve increases. This point not clear why ever so good points, to more, and decrease constantly increasing current in a mixed state between convection regime and boiling regime, and here again increase. So if we use, for example, wire of 500 micron, for example, mechanically, we don't have a ratio of 300, but just 3 or less, so almost nothing. But also, if we increase the temperature of the bath from 20 Celsius to 60 or 80, this flat region starts not at 1 ampere, but here 300 milliampere. So better to go at higher bath temperature. And when this is the loading of the wire, the resistance increase. So this drop we gain in voltage. So even better. This curve can give us a suggestion how to optimize the ratio between the voltage applied and temperature. It is another experiment with light water. We want to understand what happens in hydrogen light water. We produce high voltage, low current, so the lithium concentration is 10 units per about. And we increase the current, and this again, here was loaded at some good value, 1.42. We increase current, and the loading increase, but after some critical point, it started to decrease. So we reduce again the current, but just the loading. So when the system go out, we have almost nothing to do. But this loading is good because we coated the way the surface with the kappa, did about 1 micron we estimate, and leave some calcium and magnesium on the surface like sponge. In this experiment, the less cathodic, unfortunately, is better than most cathodic. Means this experiment never can give a chest. I will skip because time. The first experiment, loading with high current and low voltage, what usually people make. So we have experiment where it is very easy to have large loading in a short time, but if you observe the loading is less than previous, just 1.62 instead of 1.42 acceleration. Very easy. But we have a saturation, so if you increase the current over this value, 400 milliampere, you just lost energy. So so not good over some limited current, saturation. But when you decrease immediately the routing. So we think using large current is easy. All is expected. The most cathodic was better than less cathodic, but the loading was poor. I skip another. Shortly is our new calorimeter. Okay, it's more compact. We have the tube of 2 meters water inside pallets, and it's about 4 meters. And the response system is 2 times faster than the previous experiment, the previous setup. So the post anode use Palladium 2 to avoid Palladium coating. Is some tube covering the Palladium in order to have enough lithium in the solution, but with a low conductivity. Is the first version out of the looks. So 59 Palladium, tube, meter, and so on. Using the calorimeter, developed, all computer controlled, and just look at our latest result forming. For some limited reason, we are going to apply very large acid current to misuse the resistance. For some just limited reason. And you work at a lower frequency than our usual, so only 1 kilohertz. And what we found, we observed several times, that is, when we switch off the system, the maximum of the resistance don't go to about 1.8, but increase once up to 1.89. So it means to take the enrichment of the order of 45%. It's a completely unexpected result. So we studied a little bit about, we found this depends upon the frequency of the system, main frequency, and the shape. With the sinusoidal shape, this effect almost disappears. It is some tension, or under about 20 milliampere RMS, the effect is almost not detectable. And moreover, the other just last result, we assembled the system with a long covering 7 centimeters in heavy water, and in respect to the calibration and equilibrium, we get about -2 watts, so it's strange. In the latter, slowly it is up to 4 in 10 hours. So what we think, we have again the problem of boiling film, some section of the wire where the Jesuit happened. Conclusion. Okay. The best result reproducible with the covering nitrogen 1.58, with hot covering 1.64, the cold covering 1.2, but just one get. And there is some good effect of partially covering the surface with copper, calcium, and so on, 1.42 kilograms. And moreover, there is another effect. We optimize, we increase the thin protection, and we get 1.32 two times. So if I want to say that people, the work is in progress, please just continue.
Well, thank you, Dr. Celani. This paper is open for comments, discussion. Well, people are collecting their thoughts. Apart from the low resistance ratios that you observe, what other evidence do you have for the existence of a gamma phase?
Another is Okay. In one experiment, we covered the center, the wire, with with the screening tube, and so this section cannot be deuterated, just moving by electron migration. So when the side back get a large loading, the speed in this covered section increases. So can be this reason.
Frank?
Yes, Michael Schaefer, General Atomics, USA. This is a question about technique, really. It seems to me that you are trying to optimize loading as determined by the resistance ratio. And my question is really, you are pulsing this palladium wire through very large current pulses which yield very large temperature cycling. Wouldn't this lead to damage to your palladium, and therefore the resistance might be a measure more of damage than of loading?
Okay. When used before the pulsing condition, we realized that the pulse is so short in time that the real increasing of energy was very low. So we have a lucky condition, just with luckiness. We have very large voltage drop and definitely temperature very low because input capacitance was 1%. So this ratio that we showed can be 10 times larger. Moreover, to get CFE, we check in some non-equilibrium condition. Without non-equilibrium, according to us, nothing. Or just few effect, few percent, people will always blame, oh, maybe error.
Professor Fleischmann.
Just to come back on that point you made, if you look at the kinetic experiments we had in the Mao meeting, which is ICCF-7, you can see that you can throw the gamma phase by electron migration towards the end of the wire. You can make a device loaded, you push the gamma phase. It's like a soliton, really. And that really gives a key on how you might proceed with this. But I want to ask Francesco,
yes.
Have you integrated this at all into the Aharonov concepts, or
yes,
is it early day?
Okay, maybe Bob Marmon's effect, as developed from you and Giuliano Parata, can work, but what just my estimate with, I can put it better maybe with short wire. It seems that you cannot have as long as you want the wire.
Well, the question is how long is the coherence domain and how you should structure the wire to make
I just have seen comparing with wire between 5 centimeters and the 25. The 25 is better than 5.
Yes.
But we make a longer.
It's not
I think that something else. Maybe make a problem. I don't know. Maybe in principle it's good.
I mean, the coherence domain is astonishingly big.
So I use the 4 meters because I hope this system can help. But really, I don't know which one is the limiting because some little damage on the wire, any reason, so the current is destroyed. So it's good principle in theory, but how to really make useful for our to get your feet need more work. Okay.
Dr. Morrison.
In your final transparency, you gave your result, the best result, as 1.32 times R0.
Yes.
What is that in the loading of deuterium over palladium?
No, it's hydrogen. It's hydrogen.
Hydrogen of deuterium.
About more than 1. So really big number according to the curve that I have also give me Mike.
Tom.
I just wondered about the strategy of trying to use the resistance ratio as a criteria of progress. It seems to me that if you have a high temperature region of the wire and a big temperature comes to the water, that might be an indication of getting excess heat. And that's really what we want rather than loading. So is this really the proper strategy to pursue?
don't understand really.
Okay.
No, you said, so,
Can you help?
can you rearrange this? The question, my English is not so good. Sorry, I'm Italian.
It seems to me that your strategy has been to get the largest loading is indicated by resistance ratio.
Yes, so large loading is a necessary condition, but it's not all.
Yeah, you don't want to
What
get
what we
too
want
large.
to get the loading is just starting point. And we have to move in some way, maybe chaotic way, I don't know. This deuterium to increase the locally the loading for some physical value. So I think just mean value for loading is not so much important for chassis. In one experiment, I want to say again, in 94, 93, using plate, when plate we get a stable loading about more than 1-to-1. So, but when we watch for heat, we realize that during the loading, we have some chassis. In stated condition, even 1-to-1 in the hotel, the heat completely disappears, 1-to-0. So this experiment can give us strong information about. Maybe the local loading is not 1-to-1. What we need might be 1.2, 1.3, something like that. So this is the reason why the non-equilibrium helps. Because we have locally very high concentration.
The real measurement, I mean, it seems to me the end of the wire that is giving the most heat may well be the
Yes.
end of the wire where you have the largest delta T,
Yes.
and where you think you're losing your
Anyway,
hydrogen.
I have some interesting information from my friend. They make some equivalent experiment, and they use several shrinking along the wire.
Yeah.
What they get, the apparent heat is negative. So it means locally the temperature go very, very large. So the calculation about 1 cubic centimeter, 4.2 joules, is very wrong. Use 2,000 joules. So more complicated situation.
Yeah, I just,
So maybe necessary to recover completely the heat. And the novel system is difficult.
seems the boiling is a sign of success.
Yes, locally boiling can make fast result.
Okay.
So they need more sophisticated calorimeter to recover. Okay.
Dr. Thompson?
Passell
Yes,
fire. I wondered if you understand, did I understand you properly that the light water case actually gave you an excess heat event? And if so, then you attribute that to the fact that you
Okay. Well, to come back.
concentrated on the
Okay.
material.
I want to come back to this point. 2 years before, we started a system with Palladium. Palladium alloy has the property of very fast diffusion speed, intrinsically. And we make experiment in comparison with light water and heavy water. So, and compare with calibration. What we found, after not so long time, that even light water system gives some chassis, less than heavy water. But that time we did not understand why it's so strange. So we think wrong calibration, something wrong happened. But now, looking to the problem, to the effect, that in proper condition it's possible to enrich the value of the Palladium wire. Maybe this can be the reason. So not the wrong limited, we should get experiment with Palladium, but something more sophisticated.
Thank you very much.
Well, I think we can close the discussion at that point. Thank you again, Dr. Celani. The next paper will be presented by Dr. Asami, reporting on work, extensive work, performed at the Hydrogen Energy Laboratory in Sapporo. The title of his talk, and a topic very close to my heart, is materials characteristics of highly loaded deuterated palladium.
today about recent activity on material development at our energy laboratory entitled Material Behavior, Highly Integrated Palladium. And this R&D has been conducted by the financial support of Japanese government and legal. And as a background of this R&D, it has been proposed energy phenomena is dependent upon parametric characteristics for usual law. And usual high loading condition is necessary for attaining high reproducibility. Therefore, our material development has proceeded according to these postulates. And our objective of this R&D is to modify material processing and treatment to attain high loading, and to find suitable electrolysis conditions, and to study loading and developing mechanisms. For this purpose, the following experimental technology, namely following items, has been developed and applied. Deuterium loading experiment using electrical resistance cell and gas chromatic analysis, and high pressure and high temperature gas loading, in situ observation of palladium during electrolysis, and in situ X-ray diffraction experiment. Regarding to the deuterium loading experiment, the first item is dependent on palladium purity and processing. The objectives of these items is to material improvement by grain size control, purity control, and surface treatment.
Qual addirittura sto scrivere tutta, si mangia le scrive, non sempre quando finisce, con tutte le cose.
The grain size control is generally available to introduce forging and homogenizing process during metal processing procedure. This process is a typical example for processing for palladium 49 palladium. This site is rather simple. However, forging process and homogenizing, one homogenizing process is applied. And second process, in this case, a fourth homogenizing process is applied. And for grain size control, for the small grain size, 650 centigrade in vacuum is applied, and for middle grain size, 1000 centigrade, and large grain size, 1100 centigrade in vacuum. Microphotographs is the structure of the size, middle size, large size for 49 Palladium. This is for 39 Palladium. For compare this and this, the 39 materials is more uniform. This figure shows the loading experiment. The upper side is R over R0 change, bearing electric stage and times. And look the final stage of the loading, the difference between among the length size, three length size is obviously observed. Middle size was small size is better than larger. This figure shows also the loading behavior. Also look at the final stage of loading. Medium size is better than other. This is for 39 Palladium. The conclusion of these items is forging and annealing process bearing processing is effective in attaining uniform length and size Palladium materials. And this size is easier to control for purity of 39 Palladium than 49 Palladium. The final maximum attained loading is similar for both 49 and 39. And the effect of blend size on loading for the 49 Palladium, smaller blend size is better than the large. And for 39 Palladium, no clear difference by size, but middle size is better than other size. Second item of the Deuterium experiment is the effect of heat treatment, surface treatment, and electrolysis conditions. As the objective of this experiment, to optimize heat treatment temperature and surface treatment method, and to optimize electrolysis cycles. Here shows the also loading behavior for the several three stages of loading. And look here, the difference between the surface treatment method is clear appear. For the terminating acrolegia is better, or HP 1 minute is better than other treatment. This figure shows final treatment of the annealing temperature between attained loading ratio. And the suitable annealing temperature 900 or 1100 temperature is better for other conditions. And look this final stage of the loading. This great frequency between the among the current density and other factors is smaller than other states. And about the current density of 3 milliampere to 200 milliampere per square inch is better performance for other conditions. Conclusion of this experiment, high vacuum annealing at 900 to 1000 centigrade is suitable for attaining high loading. Pre-etching by aquaregia for about 10 minutes is effective for removing surface impurity and to attain the high loading. The step-up current cycle up to 3 stages are effective. One cycle or 2 cycles are not sufficient to attain high loading. And anodic treatment between each cycle is also effective for high loading. Okay, to explain. First stage and second stage and third stage of loading process. During this stage, we apply the anodic treatment. The next items is behavior during Deuterium loading measured by gas chromatic analysis and Anomalous measurement. The objectives of this experiment are to clarify the behavior of Deuterium loading during temperature change, to determine the temperature coefficients of the plug-in systems, to observe the correct relation between alveolar and gas chromatic method for the loading ratio. This figure shows a schematic diagram of loading experiment by gas chromatography. The SRI type DOL cell is used for this experiment. The gas sampling is every 5 minutes collected. And next figure shows detailed data. This relation between elapsed time and loading Deuterium. And this curve is, red curve is measured by gas chromatic analysis. The upper side of the details of the loading, upper side, this is oxide, real oxygen generation. It is corresponding to loading. And downside shows hydrogen generation. It corresponding to the deloading. We integrate these gas generation and calculate this red curve. And loading and deloading behavior of details is observable like this. hearing loading. Here, 20 degrees, 40, 60, 80. The loading behavior is done according to the temperature rising. And here, when we rise the temperature 20 to 40, the loading goes down. And after that, loading is small loading is again occurred. And again, 40 to 60, the loading fast and loading. The loading, the details of the loading or the loading behavior is observed by instruments. The conclusion of this experiment, loading ratio measured by gas chromatic analysis agree well with those measured using the resistance method. Detailed structure of loading and deloading behavior was observable by gas chromatic analysis. The loading analysis of Palladium decreased with the rise of temperature and it increased with the drop of temperature. Despite heat input at high loading stage, loading ratio decreased. This method was originally proposed by Deuterium or Iwamura of NAS. By this method, this figure shows Palladium D Asami diagrams. This region is the alpha plus beta region. High temperature and high pressure gas loading is made attained by this process, lead dotted lines. So we don't exclude the alpha plus beta phase by this method. About 0.62 to 0.68 loading ratio is attained by gas loading, high temperature and high pressure gas loading. This is a typical loading behavior of gas loaded. Blue line is gas loaded, and green line is electrochemical loading. After the fixed loading stage, the difference is clear. Gas loading is better than chemical loading. This is a microstructure after electrolysis loading. This is the ordinary electrolysis procedure. We can see the many split bands inside the grain. But however, we cannot see the much deformation defect for the high pressure and high temperature loading. This figure shows the excess heat measurement by using high local humidity systems. this green curve shows the loading ratio. And this is the current change and density change. And this is the excess heat. Unfortunately, we cannot observe the excess heat. But the loading ratio up here, this one is 0.96 by SRI scale. So we like to conclude this experiment. The loading ratio, loading load, which were loaded in deep gas at high temperature and high pressure were approximately 0.62 to 0.68. Even after this zone gas load specimen, they keep their straight shape and surface smoothness. However, different loading behavior and attained maximum loading ratio was similar to that of ordinary electricity. So I must have many, I remain many photographs for figures to explain. I got time.
The papers have been the discussion. As people are walking up, I must say that since I'm familiar with the work that was done and the difficulty of the experiments, it's reported on an extraordinarily detailed and extensive examination, which I think will contribute valuably to the metal hydrogen literature. Professor Pons.
I'd like to make two comments on this valuable paper. First, a general comment that the investigation of material properties, I think, has become a focus this meeting, very important. But I want to stress the importance of looking at the surface of the electrodes in detail as a function of time. As you go on, and the electrolysis goes past 10, 100, 1,000 hours, enormous amounts of material aggregate on the surface of the electrode. There are various spectroscopic methods for dealing with this and analyzing it, and it's very important because it affects the fugacity of the hydrogen inside the electrode. It's not only the surface, but the desorption mechanism of the hydrogen emission reaction changes, and therefore, as the impurities aggregate, the fugacity inside changes, and this, of course, affects the environment. The other general comment I'd like to make about material properties, the great importance of looking inside the electrode and layering it, taking it down 1 micron, even maybe 10 microns, and finding out what the damage is as a function of the potential time and the rest. One of my students has done this, and find that even with an over-potential of 0.2, it's a very low over-potential, damage begins. And so you have these fissures and holes, very high pressure indeed, perhaps 3,000 atmospheres, 4,000 atmospheres. These are the things, I think, that we have to look at inside. Thank you.
This question concerns the X-ray diffraction data that you took during experiments. Did you see any evidence for a gamma phase from the X-ray diffraction?
I'll actually do the evidence of X-ray diffraction. This is a measurement system dealing electrolysis. X-ray is comes on this side and dealing electrolysis. This cell is pressurized at 9 atmospheres to prevent bulk formation. And P by PD ratio measured by electrical release. And for your questions. I explain this video. This is a drawing about 0.6. The palladium bead and attach the surface as a reference to capture electroplate. And much higher loading ratio, 0.918. Also, only Palladium D beta field. Unfortunately, I cannot find the new plate or gamma plate.
Thank you.
Good job.
Can you please explain why it is the recrystallization rate for 3,9 palladium, which is less pure than 4,9 palladium, is higher? Normally it should be like so. Once again, from the photo we showed, it looks like the recrystallization rate for 3,9 palladium, which is less pure than 4,9 palladium, is higher. And normally, the more pure metal you have, the higher the crystallization.
The question relates to the recrystallization rate. Your data seems to indicate that the recrystallization rate of the impure material was faster than the pure material, which is contrary to experience.
I think the surface energy of the grain in nuclear material is lower than the hydrogen material. So the annealing process is easily to attain or treat the nuclear material. So the uniformity of the diffusion in the raw material is more uniform for the material. So the uniformity is more good for the
Dr. Passell.
So we know the exact impurities in the green ions material, the elemental impurities and their concentration, the elements that constitute the impurities in 3 nines and 4 nines. Do you have a list of the elements and their concentration in those impurities in your sample? In other words, where are the impurities? Do you have a list of them?
I believe the 3 nines material was intended to emulate our Iwamura Lot 1, is that correct?
So we make many kinds of green materials. For example, we have the layer number 1 lot measure that kind of material. Another utility model material also made of green. They are many.
Yeah.
But this kind of phenomena, homogeneous,
chemically assisted nuclear reactions, aka cold fusion, is the lack of reproducibility. And fortunately, a number of the techniques for producing the effect have now become reproducible, so we have fewer problems. However, the Pons Fleischmann effect is still not reproducible. And we know now that that is caused primarily by the palladium itself. So my efforts have been directed towards trying to understand what it is about palladium that makes it non-reproducible, gives it this unpleasant characteristic, and also develop simple techniques for measuring or for determining which palladium is good and which palladium is bad, so we don't have to waste a lot of time looking at bad material. I'd like to give you some of the insights and results that obtained from that effort. It's necessary, as we all know, to obtain a high composition. The composition is obtained by the competition between the rate of gain and the rate of loss. These two are separate independent properties and need to be determined separately and independently. So I have looked at the rate of gain and measured that in terms of the loading efficiency, which is the ratio between the number of atoms of deuterium that are going into the palladium divided by the number presented to the palladium by the current at any particular time. The achieved composition, we measure the average composition, the bulk composition. This is clearly not where the nuclear reactions are occurring, but it is something that is required, that is, you have to get a high bulk composition in order to obtain the high composition that is present in those regions where the nuclear reactions are actually occurring. They are occurring on the surface, and to get at the surface composition, I measure the open circuit voltage. This is the voltage between the circuit, or between the cathode and a reference electrode when no current is flowing through the cell. And this voltage is proportional to the Gibbs free energy of hydrogen in the surface of the palladium. I also have some direct measurements of surface composition that I'd like to show you, which give a little better understanding of what the true composition of the surface might be. And next, the rate of loss. Deuterium is lost from the palladium, and it's lost continuously, even when it's fully loaded. It's continuously being lost. And the question is, well, how is that happening, and how can we control it? I measure that by plotting the deuterium loss versus the square root of time. That's a linear relationship indicating that the loss is diffusion controlled. All right, so let's look at some of the experimental relationships. This is the loading efficiency versus the average composition. And you can see that the loading efficiency is dependent upon the treatment. Untreated material, it starts high at high efficiency. In other words, every atom, practically every atom that's presented to the surface is dissolved, but then it drops rather precipitously and finally goes to zero when it's fully loaded. However, if it's treated with aphoresia, you can see that it stays high for some period of time while the alpha is converted to the beta phase and then drops down. This is the character that one wants to have. And by applying this kind of measurement during loading, you can determine whether or not the material is going to have any hope of producing excess energy or achieving a high composition. The loading efficiency is also dependent upon the applied current. At low currents, it's low and it goes and saturates at higher currents. This indicates that there are two processes occurring on the surface. One is very efficient. It's allowing the deuterium to go back into the solution, but that becomes saturated at higher currents. The open circuit voltage is very interesting. If you follow the open circuit voltage as a function of loading, you find that it rises as you saturate the alpha phase. It remains constant in the two-phase region as you expect it to do, and then it starts rising again when the beta phase is formed. So it does follow the thermodynamic behavior of the bulk material. And that indicates that under low loading conditions, there's very little gradient between the surface and the interior. However, if you go to higher currents, you can see that there is a gradient and this ideal relationship breaks down. If you deload, you get the reverse effect. It drops down as the alpha phase, or as the beta phase converts to the alpha, and then you get the two-phase mixture, and once all the beta phase is gone, it drops precipitously to zero. Once again, following the thermodynamic behavior of the bulk material. This is the curve that's most interesting because it shows the relationship between the surface composition, or indirect relationship between the surface composition and the composition during deloading, but in the beta phase. See, this is the beta phase coming down. This is somewhat typical. The beta phase deloads, and then it goes two-phase and becomes constant. The shape of the curve in this region is very important, as you'll see. This is the same kind of deloading, open circuit voltage versus time, but this material was making excess energy at the time it was deloaded. And you can see an entirely different behavior. It drops down, and then there's a rest, and then it drops down again. It continues on. All of this is still in the beta phase. This indicates that when excess energy is being produced, another phase exists on the surface other than the beta phase. And that will decompose slowly if the current is turned off, and then convert to the beta phase. It's this material that we're looking to produce, and it's the absence of that material that allows us not to produce heat. You have to make this stuff if you're going to make heat, and it's very difficult to achieve sufficiently high composition to do that. Deloading follows this is the average composition versus time, square root of time. It's a linear relationship. In this region, you're deloading in the beta. At this point, the alpha phase forms, which has a different diffusion rate, and so it has a different loss rate. The slope of this curve is an important property. Also, that curve, the one you just saw, it was deloaded in the electrolytic cell. This one here was deloaded in acetone, this one was deloaded in air. They all have the same effect. They're linear and they're almost the same values for the same sample, indicating that the deloading is not occurring through the surface. That is, the surface is presented to these liquids. These liquids will change the character of the surface and therefore the deloading rate if that's where the deloading were occurring from. It's occurring from cracks inside the material which are not in contact with the liquid. Now, samples have two basically different properties with respect to deloading. First of all, the deloading is dependent upon the composition from which you're deloading. And that relationship roughly follows the behavior of the pressure that you would calculate to be inside the cracks of this material. Of course, there's a slight deviation here because there's a gradient within the material, but you can see that there's a basic relationship there. This is ordinary material. Occasionally you have material that deloads in this region, and the deloading rate there is much less than what you'd expect based upon the composition. It's this material that has the potential for making excess energy. This material does not. Let's see, the composition limit is temperature dependent, as we all know. This just shows the relationship between the composition and the electrolytic temperature, and that's the primary variable. These are done at two different currents, but if you plot it in terms of temperature, it makes sense, but it doesn't make sense if you plot it in terms of the current itself. So temperature is far more important than current, but when you change the current, you automatically change the temperature, and that's what you're primarily seeing. Now, I have measured the composition of very thin films. This is 2 microns of palladium on platinum. And I've plotted the average composition against the current density. This material here is a 1 millimeter bulk sample plate, and that's typical. You know, it goes up as currents increase and it saturates. But now this thin film shows an entirely different behavior. These are numerous values. Some of this is error, some of it is just differences in the composition of that particular material. But you can see compositions as high as 1.5 are achieved. At this composition, the open circuit voltage indicated that the material was not at a high enough composition to make excess energy. So the material that we're truly looking for has a composition even higher than that. Furthermore, within the 2 micron layer, this is the bulk composition, if you understand, within that layer there's also a gradient, and its surface is even at higher composition than the bulk. So I indicate that we are striving to produce a composition that's well in excess of 1.5 on the surface. And it's only when we achieve that composition that we can make excess energy. All right, some conclusions. How much time do I have? How much? 8 minutes. Oh, wow. All right, well, we're just speeding along here. The open circuit voltage, loading efficiency, and deloading rate are sensitive and easy methods to study the behavior of cathode surface. They are also very good methods to use to sort palladium into 2 piles, the good pile and the bad pile. Now, I can make that sort. I can identify very easily bad palladium. However, I cannot identify palladium that will make excess energy 100% of the time, but I can up the odds. Excess energy will not be produced unless the surface has achieved a very high composition and converted to a new crystal structure. And both of those things have to happen. You can get a high composition, but unless it is converted to that new structure, you're not going to get excess energy. And that's the reason why people have achieved high compositions and still have not seen excess energy. You have a 2-step process. And that second step is dependent upon a lot of variables, including impurities that are present in the surface in addition to the high composition. Palladium will not obtain a high composition at the surface unless the DD recombination reaction is blocked at the surface, unless the bulk material is free of cracks. So the surface character is very, very important to block this reaction, and you have to have palladium that's very strong that will not crack. And as we know, we've seen other people previously have shown that when it cracks, then it just deloads. Mike just pointed that out very dramatically, and we've seen the same thing. Most D presented to the surface enters the bulk material, diffuses to the nearest crack before being expelled as D2 gas. And that process, I say, is going on even when it's fully loaded. There's a constant flux passing through, and you just can't do anything about that. And indeed, if you try to enhance it, you're probably making a very small contribution. Now, I'd like to make one observation. It's apparent to me, at least, that you have to have this nuclear active state. You have to have a phase that is abnormal, that has properties which are different than normal material, that has stoichiometries different than normal material. You have to have that material there. And theories, attempts at explanation that focus on the beta-plated deuteride, I think, are doomed, because they're not talking about the true material, the true chemical environment in which these nuclear reactions are occurring. The other problem is that we need to know more about that environment. We need to know what we're looking for. I mean, the problem at this point is that we're looking for a needle in the haystack, and we don't know the shape or size of the needle. We have to identify the character of this new phase so that we know it when we find it, and also know how to produce it. Because presumably, if we know the structure of that phase and other characteristics about it, we can design materials, atom by atom if necessary, to create such a structure. So it would seem to me that would be one of the major goals that I would advocate, rather than just the trial and error that has been applied in many cases. Okay, thank you very much.
For discussion.
I'd like to comment, Ed, on an aspect of time. I think you've done more than anybody else to try to define these conditions. But as you know, one of the mysterious things about this is that if you use wires of 1 millimeter or something like that, 90% of the work has been done on this type of one, it takes many hours, 100 hours, or something like that, to get heat, when you do get heat. And so any analysis of the structure is going to take place in some minuscule time, like 12, 20 hours, even 50 hours, is not going to correspond to the reality of when you do get heat. And so you must do that. And then they must go for a very long time, corresponding to the time in which you do get it. The other thing is, and I think we've talked about this in our correspondence and telephone calls, cracks. There are cracks and cracks. Of course, if you get cracks large enough to reach the surface, what you say happens. It deloads, no doubt of it. And Kevin Wolf pointed this out by 1990. But you do get damage, and cracks and holes and fissures very early on, in 10 hours. And local temperature is very low, 0.2, 0.3 volts. There's already fissures in there at that time. And so one must distinguish between cracks which reach the surface, which correspond to your cracks, so to speak, and other cracks that may be very important to the actual cause and effect.
First of all, the time problem is a good one, and you have to have two things happen. You have to have good material that you can identify early on, or more exactly, you identify bad material which is never going to load no matter how long you heat it or put it in an electrolytic cell. Good material, however, will load up, and then the open circuit voltage over a period of time will slowly rise. And as long as that is rising, then you know that you have some hope in the future of making excess energy. But very frequently it will rise, and then all of a sudden it'll drop. At that point, you might just as well go home and turn off your cell and put another sample in. By looking at the open circuit voltage, you can make that distinction early on without waiting for 30 days and giving up in disgust. You can give up much earlier. The second thing about the cracks, yes, there are two different kinds of cracks. Generally speaking, they are roughly related. That is, if you have a lot of cracks on the inside, you have a certain number of them that are going to penetrate the surface. And so it's good if you have a low average number, but you do have to distinguish between the two kinds, I agree.
Heinz Rohr from Sydney, Australia. A very naive question, because you started from the irreversibility, from all your beautiful knowledge, avoiding blocking and so on. Can you simply say now that you have it completely in your hands to get reproducible heat-producing palladium?
No. Palladium is by nature irreproducible. I mean, that is the nature of palladium. Just like it's the nature of some people, palladium has that characteristic. Now, you can sort bad palladium from good palladium, and you can do some things that can encourage it to be good, but I don't think you can ever really make it perfect. And for that reason, I don't think palladium is ever going to be the answer to our problem.
Two things I don't understand. On your identification of new phase by overvoltage, I don't understand how you can tell the difference between metal deuteride and some kind of silicon coating or lithium coating, or God only knows what else might be on the surface. The second thing I don't understand is if you've got a loading of 1.5 near the surface, question is how did you figure that out? For example, if there were X-ray diffraction or neutron diffraction resistance ratio measurement that would support that. That would be extremely interesting. I don't understand what your measurement was based on to get 1.5. I don't know what it means for the bulk loading.
Well, the answer to the first question is that the voltage is created by a chemical reaction, and if something goes onto the surface that is capable of producing a chemical reaction, therefore a transfer of electrons, you'll see a voltage. Hydrogen is the most active of the various materials that are in this material, and so you're seeing that as a dominant reaction. Now, other materials are there and can interact with the solution to produce a chemical reaction. You'll see those voltages as well, but they're generally small. They're wiped out, overwhelmed by the hydrogen reaction in these systems. And if you load and then deload, it goes back down to zero. Now, if there's an offset there, yes, that's probably because of some impurity on the surface. The method of loading is the oil displacement technique. It's a sealed cell with a recombiner in it. The organic oxygen accumulates, displaces oil onto a balance, and this is oil is in this. Displace it onto the balance. You weigh the balance, and you can calculate the composition. This is sufficiently accurate that I can measure the stoichiometry of 10 milligrams of palladium with a certain amount of air, of course.
Yes, yeah, Scott from NRL. As a follow-on to what Peter was saying, I appreciate what you say about the hydrogen being the most active of the chemical ingredients in this sort of thing. But to say that there's an entirely new phase is somewhat deceptive. Are there other parameters that could be measured that you can think of besides this voltage to characterize what's happening at the surface? I mean, the gradients of the concentration or some other parameters?
Yes, there are other parameters. The problem is that it's very difficult to apply very much any other parameters to this. For example, X-rays has been made to produce this and look at it with X-rays, but the geometry does not lend itself to the conditions that allow you to get to these very high compositions. I mean, it's a heroic effort to get to these compositions even under the most ideal circumstances.
Yes.
The other technique that I have hoped to use and will attempt to use would be magnetic susceptibility.
Yes.
That I can do in my cells, and if that changes or if they become superconducting under these circumstances, then I should be able to see it.
In fact, I mean, that goes along with some of the things that I was saying in my earlier talk. I mean, I think that there really would be a gradient concentration, especially at very low temperatures. Thanks very much.
Seconds. Huggins from Kiel, Germany. And this is wonderful work. I wonder if you have done any experiments which you had a sample with an initial high open circuit voltage, you let it deload, and you loaded it back up again. Have you seen the open circuit voltage go back up into the range it started?
Yes. It's totally reproducible. You can go down, you can go back up, you can follow it any number of times. However, each time you deload, it damages the material to a greater degree, and frequently you can't get to the same composition as you did before.
If you're looking for additional methods to use to evaluate what's happening, you might think about microhardness. We did some measurements a number of years ago in which we showed that loading and deloading a number of times increased the microhardness immensely, which means you're getting very large dislocation densities, which may be why you measure high loading. And a microhardness can evaluate this, and what you find is you can get a higher dislocation density and a higher yield stress in palladium electrochemically by recycling it, running hydrogen in and out, than you can by cold working. And that's an amazing effect, and this may be very high dislocation density, then of course leads to local hypersaturation. And this may be why you're seeing an unusually high total hydrogen concentration.
Last question. Ed, you showed the curve of open circuit voltage versus composition, and you deduced from that that you have a second phase of so-called gamma phase appearing. But I wanted to warn you that it's very possible to have a fairly sharp rise in activity coefficient as the available interstitial sites are filled up. It's easy to show that thermodynamically that if you have a finite population of possible sites, as the atoms occupy more and more of this finite population, the activity coefficient rises very steeply. In fact, activity can go to infinity theoretically as the possible lattice sites are approaching complete fullness. Therefore, that change of scope is really not necessarily an indication of a new phase.
I suggest that these go to infinity only in theory. In practice, what happens is nature anticipates that possibility and converts to another phase. Yeah. And it's that other phase that this beta phase is converted to that I think is the nuclear active one. The other thing about it is that the open circuit voltage, although not an absolute measure of composition, it is a relative measure, and I find that I have to be above a certain value or I do not get excess energy. Below that value, I do see it. Below the value, I do not see excess energy. Above the value, I do see it. So there is a cutoff there.
Independently of that, however, it's just my warning, the activity coefficient can rise and take sharp slopes in a single phase.
Okay.
Well, let's thank again Dr. Stowe. The next paper will be presented by Dr. Iwamura of Mitsubishi, entitled is Detection of Anomalous Elements, X-rays, and excess heat induced by continuous diffusion of deuterium through multi-layer cathode.
Iwamura, Mitsubishi Heavy Industries in Japan. And I'd like to talk about the detection of anomalous elements, X-ray and excess heat induced by continuous diffusion of deuterium through multi-layer cathode. We have been studying on cold fusion to investigate its potential as a new energy source. And at first, we performed gas loading type experiments, and we considered enough diffusion flux of D is an important factor in addition to high DY/PD ratio. And we examined the palladium material by EPMA, and we thought that certain impurities play important role to induce nuclear reaction. So now we have the assumption that this necessary condition to induce nuclear reaction in solids is high D/PD ratio and enough diffusion flux of D and the existence of a third element except palladium and deuterium. To satisfy these conditions, we developed a new type experimental device and a cathode. Here shows the features of our experimental method. The first feature is that the experimental apparatus is made to induce continuous diffusion of deuterium through palladium. Here is the palladium cathode and the platinum anode. We have an electrolyte on the upper side of palladium, and we keep vacuum condition and the palladium on the vacuum side and under the palladium. And we deuterium atoms are loaded by electrochemically on this side to this side. With this configuration, we can provide enough diffusion flux of deuterium. The next feature is the structure of multilayer cathode. This figure shows a cross-sectional view of the multilayer cathode. It is composed of palladium seed and calcium oxide and palladium mixed layer and palladium thin film. Calcium oxide is introduced based on an electron-induced nuclear reaction model proposed by us. And about the model, it will be published in July in the Journal of Fusion Technology. And here is a cross-sectional view of experimental apparatus. 1 molar D2O-LiOD electrolyte and the vacuum chamber separated by the palladium cathode or multilayer cathode. Deuterium atoms are loaded from the electrolyte side of palladium to vacuum side of palladium. And the atoms are pumping out by this molecular pump. Excess heat evaluation is performed by flow carry method. And we 3 NI detectors are equipped and 1 helium-3 detector. This figure shows the separation of electrolyte and vacuum. And this yellow sheet is palladium cathode, and this circular mesh is an anode. Only this circular part of the palladium, deuterium atoms pass through to the vacuum side. And we use a O-ring gasket, current, which is resistant to alkaline solution. This photograph is our experimental apparatus. Electrochemical side part of our experimental apparatus is made of Teflon. And the other part in the electrolyte side also are made of Teflon. And these all experimental apparatus is located in a clean room. In the clean room, dust concentration is kept very low, and temperature and humidity are controlled at a constant level. Then I will show you the experimental results on normal palladium experiments. Here, this chart shows a normal palladium sample preparation. We wash the palladium sample with acetone and anneal at 900 degrees centigrade for 10 hours and vacuum condition, and the sample is cooled down to room temperature. And we wash the sample with D-based aquaregia. These photographs show the difference between electrolyte and vacuum side of palladium cathode. Figure A is the electrolyte side of palladium. This black circle corresponds to the shape of anode, and this black circle is a place where deuterium atoms pass through. And on the surface B, no deuterium atoms pass through. On the other hand, vacuum side of palladium looks clean. Its appearance is the same as before an experiment, independent of deuterium passage. We analyzed the black circle and the other point, and we detected titanium atoms on the black circle. And this figure shows WDS spectrum for the surface of electrolyte side where deuterium atoms pass through. Here is the point of analysis on the circle. We can see that the titanium and the palladium atoms peak clearly. On the other hand, we analyzed by the same method this point on the electrolyte side of palladium. We can see only palladium peak. So then we confirmed the titanium atoms by the other method. Here is the example of the analysis. Upper figure shows the EDS spectrum, titanium here, and the lower figure is the XPS spectrum. Also, we can see the titanium peaks. And furthermore, we analyze by OJ electron spectroscopy. We see also titanium peaks. And lower figure shows the Dex profile obtained by OJ electron spectrum. We can see that from the surface to 3.4 micrometer, titanium is a major element. And at this point, palladium atoms increases. And next, I will show the impurity analysis of electrolyte and platinum anode. These values are obtained by ICCF method. We can see that the titanium concentration is very low. The other impurities, such as aluminum or silicon and iron, is high. So we discuss on the contamination issue of this titanium detection. Before electrolysis, we analyze electrolyte and platinum anode and platinum cathode, and we estimate maximum titanium mass in the experimental apparatus, 22 micrograms. But on the other hand, after electrolysis, we analyze the black circle by ICP mass. And we estimate that titanium mass is 21 micrograms. So detected titanium mass is nearly equal to the maximum titanium mass contained in the experimental apparatus. As shown in the previous table, there's a much higher concentration impurities such as iron or copper and silicon. But these elements are not detected in this case. Only titanium atoms are anomalously detected. We think that selective contamination of titanium on palladium is difficult to assume. So the detected titanium cannot be explained by contamination. It is suggested that titanium formed by nuclear reactions in solids. Okay, let's move on to the next point. This figure shows the chart. This chart shows how to make a mercury cathode. We wash the palladium sample with acetone and anneal and wash with the apparatus. And after that, on the palladium sheet, calcium oxide and palladium mixture layer sputtered by simultaneous sputtering of calcium oxide and palladium. The thickness of the mixture layer is 1,000 or 3,000 angstrom. And after that, by using ion beam sputtering, we formed a palladium thin film to avoid dissolving the calcium oxide into the electrolyte. And this mixed layer is put at near the surface because we think that the nuclear reactions occur at the near surface. And this table shows the summary of multi-layer cathode experiments. We summarize on structure of cathode and excess heat and X-ray and detected elements after experiment and mass 57 by mass 56. Sample 50, 51, 52, 53, 61 all belongs to multi-layer cathode. In the table, sigma is a standard deviation of the background. And the background data is obtained by the light water experiment. EV54 is a sample of the light water experiment. We can see that all of the cases for multi-layer cathode, we can detect the excess heat and X-rays. About X-rays, X-ray 2 and 3 are simultaneously detected. And this value is a peak value. And in this column, we show the detected elements after an experiment. We analyze by EPMA. But silicon or iron and copper is a high concentration impurities in the electrolyte, so we cannot distinguish between contamination and nuclear products. So we apply the SIMS analysis to the item, and we get this data. Mass 57 by mass 56 is related to the abundance ratio of iron. If any other impurities do not exist, this value is equal to iron 57 by iron 56. So if we analyze every iron standard material, this value is same natural abundance. It is noticeable the mass 57 by mass 56 are larger than standard material. And these values vary, ranges from 0.036 to 0.66. And this is an example of excess heat generation. Time and excess heat is plotted. At this point, making up the current up to 3 amperes, we obtain the excess heat like this. This dotted line is a 3 sigma. Next figure shows the example of X-ray emission. Upper figure